My name's Tom Otvos, and tonight I'm going to talk to you about thin meniscus mirrors and how they're a new technology that's enabling fast, large aperture telescopes. Just by way of background, and it's 3-2 for Boston right now. Like Dennis, I have kids in hockey. I have 2 boys in hockey. I'm a coach on one of their teams, and hockey just ended last weekend for us as well. So. Just by way of background, a very quickie, I'm a long time but new member of RASC. I was a member back in high school, university days of the Toronto Centre, and then life just sort of got in the way and I dropped astronomy for a considerable period of time, and then just recently have gotten back into it. I'm a member of the Mississauga Centre and an affiliate here in Toronto. And, along the way, I had a Dobsonian that, that I just kind of, up at the cottage, a nice weekend, I'd be using it. But I wasn't really actively engaged in it until a couple of years ago when I came across these thin meniscus mirrors, and I'll be showing more pictures later. But that really kind of re-energized my interest in the hobby, and specifically not just the observational part of it, but the actual fabrication of it. I don't know how many ATMs are actually in the audience. I saw some people come in, Frank and Norm were there. So there are a few ATMs in the audience, and so and some of them actually know what I'm doing. But basically, this is all about fabricating mirrors that are that can go into large aperture scopes that are highly portable. So that's the general gist of this. So what problems are we trying to solve when we're talking about meniscus mirrors? Well, basically, when you have a large aperture telescope, they're difficult and expensive to fabricate if you're fabricating them. If you're buying them, obviously they're very expensive. And typically that's because, and one of the impacts of the large mirror, a traditional large mirror, is that it has a lot of mass. And as a result, the telescopes themselves take a long time to cool down. And if you have a very heavy mirror, you need a big beefy support, which is why, with the car, you've got a 16-inch, but you need like a really big support. So one of the things that we're trying to solve is how do you make large aperture mirrors much more portable? Typically, focal ratios on amateur scopes rarely go below f4.5, and for the car we're talking about an f8, presumably the 14-inch was an f10, I guess. So much larger focal ratios. And when you combine a large focal ratio with a big aperture, you end up with a big honkin' telescope. And if you're looking at apertures, say 24, 30 inches, that kind of thing, you're talking about ladder access only. So again, that's a problem that we're trying to actively solve. So this is the question: how do you make a compact, large aperture scope cheaply? Who would be interested in something like this? Well, there's amateurs who are always, who have aperture fever, and they are always looking for that bigger and bigger light bucket to get those faint, fuzzy, deep sky objects, or to do, wide field astrophotography, or even just photometry. There are people who are not really interested in actual, fine detail, but to do photometric measurements. University astronomy departments who don't have ready access to a major observatory. They could definitely use larger aperture scopes for their research and for teaching their students. Citizen scientists, a lot of people in this audience who are interested in doing real science. And so fortunately, I've gotten myself involved with a group called the Otvos Initiative, and this was a group that was started out by a bunch of amateurs out in Oregon, of all places, and basically they've sort of mandated themselves as trying to make 1 meter class research grade telescopes easily obtainable. And so that's their goal, and they've got a number of different groups of people that are researching different areas to try and make that goal happen. So one of the ways of dealing, of creating large aperture telescopes and solving some of these problems is to use what's called a thin meniscus. And does everyone know what a meniscus is? Basically, think of a contact lens. Okay, so traditionally, your telescope mirror, looks like this. You have a really thick slab with a very gentle curve polished into it. And for, let's say, a 25-inch mirror, typically this is going to be 2 inches thick. And so if you just do the math, you end up with 100 pounds of glass. That's just the primary itself. And then you've got all of the other stuff. And because the focal length here, let's say this is going to be, an f5 or an f6, you're talking about many inches of telescope length. So you're talking about a big honking telescope. Contrast that with a meniscus, which is pictured here. This is a 25-inch meniscus created by someone called Mel Bartels, who's really one of the vanguards of this whole thrust of using thin meniscus mirrors, and he's one of my mentors and helping me out. So this is his 25-inch, which he recently actually completed. It just came back from the silvering or the alumnizing. And you can see here it's 25 inches in diameter and it's 1/2 of an inch thick. And so if you just do the math, this is 20 pounds of glass. So this is 1/5 the size of this mirror. So just from a sheer weight perspective, this is like hands down going to be far more portable than your traditional glass. If you consider focal ratio and how this impacts things as well, this table here lists a couple of common focal lengths, focal ratios, and the corresponding sagitta for a 14-inch, which is my personal project, and Mel's 25-inch. The sagitta is the distance, is basically the depth of the curve of your glass. So basically, it measures from the edge down to the deepest point. And so you can see how the faster your telescope, the deeper your sag is in your glass. And so for a 25-inch, the sag here is 0.6 of an inch. So at f2.6, if your typical blank is going to be 1 inch for a 14-inch mirror or 2 inches for a 25-inch mirror, you're looking at about 1/3 of the thickness of your blank is going to be carved away by the curve. What that means is that if you've got 100 pounds of glass and 1/3 of it in the center has been carved out, that leaves 2/3 there. So it's going to totally mess up the thermal properties of that glass, as well as structurally. You're basically making it considerably weaker there. So all of these things kind of compound. So if you're looking at a large aperture, you can't actually fabricate a fast mirror without having a whole bunch of other complications. For a meniscus, however, again, think contact lens, basically the thickness is the same for the entire length of the curve. So basically the mirror is curved front and back so that it's of uniform thickness. That means that, for one thing, it's going to reach thermal equilibrium much more evenly. Secondly, because it's only 1/2 inch thick as opposed to 2 inches thick, it's going to reach thermal equilibrium much more quickly. And then it turns out in practice that because of the curvature, it's inherently stiffer. If you think about a piece of paper that just kind of flops around, but then if you kind of fold it into a cone, it just has more inherent stiffness to it. So the curvature actually serves to make the overall mirror much more stiff, so that a 25-inch, 1/2 inch thick piece of glass, it doesn't show any sort of astigmatism when it's actually mounted, which is a very important thing. Now, meniscus mirrors aren't the only way to solve the problems that I was talking about initially. There are many other alternatives. Another way of reducing just the weight of large mirrors is to do what's called honeycomb casting, where basically the bulk of the mirror is open airspace, and they cast it in special molds. And so, for example, the Giant Magellan Telescope uses this approach, and lots of large telescopes use this. Spin casting is another approach that's being actively researched by one of the members of the ALTAZ initiative. And basically what they do is they get a liquid epoxy and then they slowly spin it on a turntable, and that naturally creates a parabolic shape on the surface. And the trick here is how do you create an epoxy resin that as it hardens doesn't actually change the shape? But that's what they're actively doing research in. And then once they've got that thing, hardened, then they would basically coat it, and presto bingo, you have a mirror. Foam glass is another material that's been explored, which is basically it's like foamy glass. It's a very, very lightweight material, and they use it, and it's very easily formed. Obviously, it's not very rigid, so it's got its own problems. All of these things are other talks, and they're all interesting areas of research, but that's not really what I'm about here. So what I'm about is meniscus mirrors. And once I got into this and started exploring this, I thought, well, hey, how hard can it be? So I wanted to tackle the project. And after seeing some of Mel's telescopes, I've got a picture of one at the end, I was just like, okay, I absolutely have to have this. Because one of my problems was I had this big 8-inch Dob, and it wasn't portable at all. So basically, it was up at my cottage all the time, so it was only accessible when I was at the cottage, which meant almost never in the winter time. So, hauling it back and forth, pain in the ass, right? So I wanted something that was highly portable. But I also had aperture fever. It was only an 8-inch, and I wanted a much larger scope. And I'd been, saving my pennies for, like a Meade 16-inch, something like that. But that's like serious dollars. So this seemed to be an approachable way of giving me a large aperture telescope in a highly portable form factor. So how does one go about making a meniscus? Well, basically, digital kiln controllers are the key enabling technology to this. And what they allow you to do is allow you to provide a very, very strict temperature control program for a kiln that then allows you to slump glass into your meniscus shape. And the kiln is just a commodity item in this case. It could be any sort of pottery kiln, ceramic kiln. The one that you're seeing here, so this basically this silver thing is the kiln, and here's the kiln controller. And this I got off of Kijiji for $100. So it like totally commodity item, and all of the magic is in this box here. While the kilns are a commodity item, form factor is a bit of an issue. Like, for example, this thing here is 17 inches in diameter. So what that means is that the most I can slump is a 16-inch mirror. And there's a ton of wasted space in here because this is this is intended for large pieces of pottery. So, when you're using ceramic kilns, you have to kind of shop around and try and find what what will work for you. But really, all of the magic is in this box. This is a close-up of the box itself. This thing here in the center is just basically it's a PID, PI. Can't think of what the PI stands for now, but basically this is like a little microcontroller, and it allows you to program it, and these things over here on the left and the right are solid state relays, which are basically controlled by the PID. So the PID just basically switches these relays on and off, and the main power going into the kiln elements are controlled by these SSRs. So essentially what you're doing is you're switching the kiln on and off, on and off, on and off, and there's a thermocouple attached to it as well that measures the temperature to a high degree of accuracy, and you just basically program it to say, here's my temperature curve that I want over a period of time, and it just measures the temperature and turns the kiln on and off, and you get your slump. Now, slumping glass, so there are really 4 major steps here to actually making this happen. So the first thing is you need to create a mold. And what that mold is going to be inside the kiln, you're going to be placing a form that is going to be supporting the glass, and the glass is going to melt onto the form. To create that form, you need to create a mold, which is basically the negative of the form, which is going to have the initial shape that you want your glass to conform to. So typically what you do is you use plaster of Paris, and you just create a blank out of plaster of Paris, and you use normal ATM hogging techniques to just kind of make the shape of the glass that you ultimately want to end up with. And so you'll have it in your head, that I want a 14-inch f2.6 mirror, which is currently what my project is. So that will imply a certain curvature, and you carve that into the plaster of Paris. Once you have that, you basically use that as a as a mold for the form that is going to go into the kiln. Now, this form is the trick here is that this thing has to be made of a material that's going to be able to withstand the temperatures of a kiln. And when we're slumping glass, we're talking about 600 centigrade, 650 centigrade. So you need special materials, and it's a secret recipe, but it turns out that the recipe is refractory cement and perlite. Now, and you don't even have to use refractory cement. You can just use we've experimented with different grouts. Basically, what you want is something that doesn't change shape as it sets, so that once you put it into your form, it's gonna faithfully reproduce the curve that you've carved into your plaster of Paris. But then you also need it to be able to withstand the kiln temperatures. The problem with just regular grout, non-shrinking grout, is that it doesn't withstand kiln temperatures. And so what you do is you introduce this perlite, which you can just get at garden centers, and perlite is a super insulator. And so what you do is you mix the perlite with the grout, and you just have the grout, just enough grout to hold the perlite into shape, and you make this goopy stuff up, and you press it into your form, and once it sets, you have something that's going to be kiln ready. I've done this several times now, and lately I've been actually using refractory cement. Refractory cement is basically cement that is intended to withstand kiln high temperatures. It's typically used for furnace repair, that kind of thing, or fireplace repair. But you still put the perlite in, because if you just cast a solid slab of cement, really, really heavy, very unwieldy. So the perlite, among other things, makes it super light. So you end up with a big form, but it's really, really light because the vast majority of it is perlite. Once you have this thing created, you put it into the kiln and you run it up to temperature to make sure that that it all stays together, that you didn't screw up somehow. One of the runs that I did, and I don't know why it happened, but when it came out of the kiln, instead of at that time I was still thinking I was going to do an f2.8, but when it came out of the kiln, my form was actually an f1.9. So that went into the garbage, but several tries later, I got something that, that actually held the curve, and so I was good to go. Then the last step basically is actually putting the glass onto the form, into the kiln, and programming the slumping cycle. And here, the slumping cycle, we're talking about 48 plus hours. So, for 48 hours, this thing's humming away in your garage or wherever you've got your kiln, and don't lift the lid, because you might scream, So it's a real exercise in patience waiting for this thing to complete. This is what my form looks like, it's actually quite smooth. It's surprisingly smooth, but you can still see little pock marks here, and you don't have to worry about those because when you just prior to putting it into the kiln and putting the glass on top, you use what's called ceramic talc, which is a super fine thing. It looks like baby powder. It looks like gray baby powder, and you basically spread it all over the surface, and it fills all of the little voids. And the idea is to make a super, a nice smooth surface on the form, and then you just place your glass blank on top. One of the things I didn't mention is that all of this work, it doesn't use exotic glass at all. Ordinarily for telescope mirrors, you're talking about Pyrex or whatever, but because they're so thin and because they reach thermal equilibrium so quickly, we've been using plate glass. So just really dumb glass that you can get from a place where you get tape glass tabletops or whatever, and they work perfectly fine. So you place your plate glass on top of your form and put it into the oven and bake it. When it comes out, it looks something like this. Anyone that's doing these meniscus mirrors, this is the trophy picture. You know, everyone seems to be taking the same shot. You know, you've got the meniscus there. You've got a bar with the digital gauge or the gauge measuring the sag on it. But you can see here, so there's a slight sag in this glass, and also there's a corresponding sag on the back side too. So basically, when it comes out, it looks literally like a contact lens. Now, that's how you make a meniscus. But if we rewind all the way back to the beginning, you know, one of the goals here is to not just make meniscus mirrors for the weight aspect of it, but also to make fast mirrors, because we also want to have large apertures in a highly portable form factor. So the meniscus allows for the constant glass thickness, and that's independent of focal ratio. But if we're talking about fast meniscuses, it's still a fast mirror, and it's really, really difficult to fabricate. So typically, you know, when you're making a mirror on your own, you start by creating a spherical shape, and then you parabolize it. And the delta in going from the spherical mirror to the parabola is usually measured in the number of waves of light, waves of green light. And typically the correction that you have to put into a sphere to make it parabolic is usually less than 10 waves for a typical ATM mirror. And if you're over, say, F15, you typically just work with a spherical mirror. You don't put any correction in at all. My f2.6 requires 39 waves of correction, and the 25-inch of Mel Bartel's has 63 waves of correction. So that's a lot of correction, a lot of manual polishing of this area, but not that area, to get just the right shape. It's a really, really difficult thing to do. Much more difficult. You know, when I mentioned that I was going to be doing this to a couple of the guys, they're going, "Oh, at a 2.6, that's going to be pretty challenging." But I've seen people do it, I know that people do it, and so that means it is doable. It is difficult. The measurement tool of choice for this type of thing turns out to be the Ronchi test and not the Foucault test. Typically, ATMers use Foucault tests. I mean, and sorry, when I say typically, I mean as up until relatively recently, when there are actually a number of really, really good alternative tests. But historically, the Foucault test was sort of the ATM tool of choice. But the Ronchi test is a much more appropriate test to use for this, because of the fact that the Foucault, because the curves are so steep, it's really, really difficult to get accurate Foucault measurements. And the Ronchi is a very, very intuitive and easy test to set up. So here's sort of an example of the two approaches here. So this is a Ronchi image. The dark lines are the actual what you see when you do the Ronchi test, and the red lines are the theoretical predictions. So basically, what you do is you look at your theoretical prediction. You look at your theoretical prediction, and you compare it to what you're actually seeing, and that will basically guide where you need to polish to get the figure that you need. Foucault, on the other hand, I guess I should have been doing this. So while you can't quantify your errors, you can certainly see where your errors are. So you can see here, you know, the curve here is not quite deep enough, and this is too sharp here. So these are the sort of the qualitative things that you get from looking at this test. Conversely, the Foucault, which is normally something that you would actually do measurements on, is difficult to do for the fast mirrors. However, you can still use it as a qualitative tool to assess your general surface shape. And so, you know, this should be spherical, this should be all uniformly shaded, and you can see there's actually some pretty grody roughness here. So it's good for doing kind of smoothness tests. Ultimately, however, you know, you do the Ronchi test for as long as you can. Ultimately, though, the final arbiter of how good your thing is to put it to the star test. And the star test allows you to really assess, you know, the level of doneness. Now, this is my star test rig that I built for my mirror. And the cool thing is, this distance from here to here is only 27 inches. So this is a 14-inch mirror, and it's basically, you know, this big. So really cool. Here's more examples of the Ronchi test versus the star test. So this is the current status of my mirror here. And you can see that it actually is doing really, really well as compared to theory. Although, you know, for example, here you can see that it's actually dipping this way a little bit. And in here it's curving a little bit in, and at the edges it's not curving quite enough. So you can see that it looks close but not perfect. And so this is the point where you say, okay, so what do I do next? Well, what you do is you star test. And the star test, so here's a star test result from this mirror here. And while the star test, you need to actually take several views and see how it transitions and all of that. So a static image isn't you know, a good here is the answer kind of thing. But you can see, for example, this bright line here should not be there, and this bright line probably corresponds to this defect in here. So doing the star test basically will give you the final word on whether this is a good thing or a bad thing. And I should have been clicking. This here, the fact that I have a nice bright ring around the edge is a good thing from a star test perspective, suggesting that my edge is actually pretty good. But this ring here is suggestive of this flatness in here.
Can I ask a question?
Absolutely.
With that Ronchi test,
Yes.
if it was perfect, would those lines be there?
Oh, no, absolutely. Yeah, the lines are there. Basically, the lines, if it's a sphere, then your lines are going to be perfectly jail bar straight. And as it becomes more and more parabolic, the lines curve more and more. And the other thing is that as you get closer and further to the radius of curvature, you get more and more lines. So basically, your goal is to find a spot outside of your radius of curvature where you get a handful of lines, so not just one or two, but like 5 or 6, and they have some good curvature to them, so that you can then look at them and empirically say, okay, well, this is good, this is bad. So the lines are always there, absolutely, and the curvature, the theoretical curves, which are these tan lines here, you can very readily predict them, and so there, for example, Mel Bartel's on his website, he's got a Ronchi calculator, and you basically input your parameters of your mirror. You say, okay, 14 inches, focal length of this, blah, 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 and then boom, it gives you your theoretical prediction. And then what you do is you take the test, you take the photograph, you overlay the image, and then you can do these sort of assessments. This was what got me down this Odyssey here. So this is Mel's 13-inch. So right now he just is completing his 25-inch, but prior to that he did a 13-inch. And when I saw this, I thought, oh man, this is just so cool. This would be so cool at the cottage. I can just put it in my trunk. One of the neat things about this is the way it folds up. It just kind of clamshells. Is that cool or what? That is just so cool. But again, this is a 13-inch, and this is an f3, so you know, a 39-inch focal length, but still, you know, very, very portable. Now, so that's sort of the end of my talk. Just one sort of sharing moment here. This is actually version 2 of my mirror. This star test rig here was missing a very important piece, and that is a clip that will prevent the glass from tipping out. And so this picture was taken last summer, and I was really, really close to being done. And obviously I was doing star testing, and I had some crappy weather, so I was trying to do some star testing with some faraway lights, and I wasn't paying attention, and I tipped it too far, and the glass tipped out. So the mirror that I'm working on right now is version 2. However, cool facts. The first mirror, to get to from where I started to tipping on the driveway and breaking into 2, was about 19 months. After about a month of, oh my God, what am I going to do? And I decided that I'm going to continue on. The approach that I decided to do was, because it actually almost literally broke in 2. There were a couple of other shards, but it was largely in 2 pieces. I used windshield glue to glue them back together, And while it would obviously not be optically perfect, it was good enough for me to then cast a new kiln mold, and then from there to cast a new form. So basically, this broke in August. By September, I was slumping again, and by January, I was in the final stages of my figuring. And so in the last couple of months have been really, really slow progress with doing this fine-tuning of the figuring. But, a 19-month project, has sort of been compressed into a 6-month. So you definitely learn, from your mistakes. And yes, the test rig does now have a tip clip on it. So I'm at star testing now, and hopefully this will be done by the summer. So that's all I have. Does anyone else have questions related to this? Frank?
Okay, so these microphones here. So let's you assemble the kiln rig. So are you now a go-to man for anybody that wants to build one?
I am definitely able to do slumping for people if they want to, and I mean I could even build the molds, but ideally, you guys could do that. But yes, I am available to do kiln runs for sure. Norm.
Hi, Tom. How do you measure your initial radius of curvature so that you can do your offsets for your Ronchi gratings to get the patterns that you presented
Right.
versus the pattern that is predicted by Mel Bartle's calculator?
Right. Well, it's an iterative thing basically, and so once you get to a spherical curve, because you'll be able to do tests to determine that it's spherical. And then once you get a good sphere, it's just an issue of moving it back and forth until you get a decent focus of your test LED on your tester, and that's good enough, at least for the initial stages. Because if you use the calculator and then you actually perturb your radius of curvature, you'll find that the predicted things don't change very much at all. So even if you're off by like a half an inch, which is pretty big, you will hardly see any difference in the Ronchi images. And then as you're iteratively going back and forth, you narrow your radius of curvature down until you're, within, 1/16 of an inch or whatever.
I have a series of questions, actually. Why would you want to do this first?
Well, so I'm an engineer, and so I like the hands-on aspect of it. Number one. Number two, as I said, before, I had this large Daub, and it wasn't highly portable, and I wanted something portable, and I saw this, and I go, oh, that's just so cool. How hard could it be? And it just kind of snowballs from there, and yeah.
My next question is, myself, personally, I look at it as saying, okay, if I need something, I go out and I buy it. I don't necessarily look at something and say, okay, you know what, maybe I can build it. Some of these guys, like you, for example, could go out and build it. Is it more of a challenge, you would say, for doing this, as opposed to just say, go buy something off the rack?
Absolutely, it's a challenge. Because, I mean, what would a 14-inch or a 16-inch mead cost? It would cost you quite a lot, and that's not money I just have kind of kicking around. It would be really hard to sell at home, Whereas I can say, hey, I got this kiln for $100, off of Kijiji. I'm saving money here, and I can go to Flintstone Glass and get my glass for $80. So all of these little things, ultimately they do add up. And frankly, one of the major sticker shockers here, so all of these things are relatively inexpensive, and it's just basically more time, that you're putting in. But there are some sticker shock elements here. Like, for example, when you get really fast, you need much larger secondaries. And I'm right at that threshold. Like for mine, I need a 4-inch secondary. But for Mel's 25, he needed I think it's an 8-inch secondary. And there you're talking about like $800-900, like a lot of money, unless you fabricate your own, which is a whole other thing. So you could actually do that too, but that just sort of adds to the time aspect of it. The other sticker shock is actually coating the mirror. And so again, luckily, at around 14 inches, it's still relatively affordable to send it out and get ultra high coatings. It's going to be a couple $100. But Mel, again, he had to pay, I think it was $1,400 to coat his 25, because 25 inches you need much larger equipment to do that sort of thing. So not everyone is set up to do that sort of thing. So in fact, this the group of people that are all sort of my mentors, and we're all kind of helping each other and learning from each other. Some of them are actually experimenting with do it at home silvering again. Which used to be the way it was done, right? Until you could, get your things alumnized. But, but one of the nice things about silver is that it is unless you get ultra high reflective coatings, which are expensive for aluminum, silver has a much higher reflectivity than your stock aluminum. So if you just get an aluminum coating, you're looking at about 87, 89% reflectivity, whereas silver, it's 95, 96, 97% reflectivity. And the only way you can get that with aluminum is to pay for the ultra high reflectivity coatings. So, but then the downside to silver is that you need to do it over and over and over again because it tarnishes much more quickly. But if you can do it at home for $30, $40, I'm good with that. So I haven't decided what I'm going to do yet, but I'm considering that too. So
My final question is, you mentioned it took 19 months to get to the first one, and then another 6 months. What have you been doing stargazing-wise in between with that scope?
I mentioned the hockey part, right?
Yes.
There's hockey, and then when there's not hockey, there's select baseball as well. So, yeah, and I was doing a project alongside this, which was to basically create a new tube assembly for my 8-inch Daub to at least make it collapsible. And so I took apart my Daub, thinking that I would make the new tube assembly and whatnot. It's still a part in a box in my workshop next to where I'm making this mirror. So I confess, not an awful lot. Occasionally, for special occasions, I'll reassemble the Daub because I still have the old tube, for like Venus transit and whatever. So, but Paul.
With that fast focal ratio, what about coma?
Okay, so you need a paracord for sure. There's no ifs, ands, or buts about it. You design it with the paracord in mind, and either use the P2, which basically sticks into your eyepiece. I don't know if people are familiar with what the paracord is. Yeah, so a coma corrector. So you can have the P2 that sticks into your focuser, and then you put your eyepiece into that. But another approach is to use the SIPs, which is another teleview thing, which basically is a paracord integrated right into your focuser. So one reason why you wouldn't want your carry-away paracord is if you have multiple telescopes and you want to put it into different scopes. But if you only ever had one, then it makes sense to potentially build it right into your focuser so that it's one less piece to carry around, and basically you just pop your eyepieces in and you're good to go.
I think it's really amazing.
Thank you.
My mind went blank. No, I know, I remember. How many hours would you say have you put into making the mirror? Not on round 2, let's say.
I haven't added up the round 2 numbers, but the round 1 numbers, it was like 19 months in calendar time, and in clock time it was about, I think it was about 200 hours of polishing. So when it comes out of the kiln, while you have the rough shape, and you typically save the hogging step of getting your rough curve, you still have to go through the process of going through the finer and finer grits, and then ultimately the polishing and whatnot. So it's not like it comes out of the kiln and you're into figuring. So yeah, but even on version 2, I was able to power through that a whole lot more quickly, because in version 1 I was getting just some weird measurements, and it turned out to be it turned out to be that my shape wasn't completely circular. It was actually slightly ovoid. And so depending on which diameter I was measuring the Sagitta on, it was differing by a little bit. And it was only like a millimeter, right, in terms of diameter, but it made a difference in the sag, and it made me crazy trying to figure it out. So I wasted a lot of time there too. But yeah, I haven't added up the clock time on hand to glass on the new one.
And what type of tool would you use for before you got into the figuring?
That just a tile tool. So basically, you would cast hydrostone, some kind of something like hydrostone or gypsum or something like that, and you embed just glass tiles, and you cast that against your glass, so that you get the right shape. And then you use that for all of the rough and fine grinding. And then once you're done with the fine grinding and you're into the polishing, then you go right to pitch lap. So that part of it is basically just like standard ATM stuff. So there's nothing magical there with the meniscus. Norm.
How are your muscles after doing all that on a 14-inch?
You know, it's not that bad, because I mean the meniscus is really, really light, and typically I do it mirror on top. So you know, you're moving a very, very small, relatively light piece of glass. I mean, you know, 14 inches is still, you know, it's like a big piece of glass, but it's only a half-inch thick, and it's just very, very light. So it's easy.
Are meniscus mirrors commercially available?
I don't think so. I don't think so. I don't think that there are any. Certainly, none of the major scope manufacturers are doing it.
Any more questions?
I should add that Mel, you know, so he just had his 25-inch coated. His next one is a 42. He's already got it, and he already has it slumped. He already has it slumped. So, you know, but yeah. So they're definitely pushing the boundaries. So you know, I sound like I know what I'm talking about. I'm standing on the shoulders of giants here. You know, I mean, these guys have done all the hard, heavy lifting, and so I'm just trying to do sanity checks, essentially, you know, to see whether it is as easy or as doable, you know, by mere mortals, you know, as opposed to someone like Mel.
I have a question. Did you
Yes.
buy the glass pre-cut, or did you cut it yourself?
I bought it pre-cut, yeah.
Okay.
Yeah, so, but you know, that's easy, because again, you just go to any glass place and you just say, I want a half-inch piece of glass, plate glass, and they'll cut it for you. You don't want them to chamfer the edge or anything, but make sure it's not the word is escaping me. No, yeah,
No.
definitely not chipped. No, tempered, not tempered.
And I have another question. Where do you send your mirror to get aluminized, or what are the options?
There are a lot of options in the States. In Canada, there aren't. The best option, I think, in Canada is in Montreal, a guy called Norman Fulham. The thing about, and I would like to go to Norm, and I've corresponded with him, a little bit about this now, but the downside is that Norm doesn't do enhanced coatings. And he feels very strongly about it, and so consequently I have to decide whether, you know, I want to go local but not get an enhanced coating, or my other short list name right now is a place called Spectrum Coatings, which apparently a number of people use. They're down in Florida, and for my glass it'll be, I think, $240 for the ultra enhanced 97%.
Place in Sudbury is gone.
Don't know about a place in Sudbury.
Word coating, is it gone? Anybody know?
He's still there, still in business. He's not doing commercial coatings because it's nuisance after his place burned down a few years ago. So he's still working on telescopes and other optics, but he's not in the commercial business of coating.
I have an online question here. What is the cool down time for the thin mirror versus the standard?
I've not tried to minimize the cool down time yet, but certainly half hour to an hour kind of thing. Like, if I'm planning on doing a star test, for example, I'll put it outside and then put the kids to bed, and then I'll go out and do my thing. Yeah, and I think that that's relatively typical of, what the other guys are seeing too. Now, for a larger one, I don't have experience with like a really big mass mirror. How long does it take for the DAO one to cool, or the CAO one to cool?
No, you're chasing the temperatures that's dropping all the time, so a really big mirror, let's say you've got an 18-inch.
Mhm.
If you're working with an 18-inch mirror, the CAO, and it's sort of a fall evening, you're probably chasing the temperature down all night.
Yeah.
Yeah.
Anyone else? Great. Thank you very much.